So today we are looking into the brain of our operation, the metallurgical digital twin. So I'm here to show you how we move from reactive firefighting to predictive mastery. So we are going to walk through the 15 slide breakdown to see how high-tech telemetry keeps our furnaces healthy and our campaign long. So coming to the advanced blast furnace dynamics. So look at this digital wireframe. We are not just looking at a shell anymore. We are seeing the thermochemical kinetics in real time. So this presentation is your roadmap for using predictive telemetry to extend our campaign life and master the internal dynamics that usually stay hidden behind the steel. So now coming to our next agenda about the campaign life span paradox. So here is the concept wise we try to understand what exactly it means. So as you know that unrecognized permeability disruptions are sharing years of our campaign. So we aim for 20-year target, but actual drift can drop us to 14.5 years, which is a massive around 120 US million dollars capex hit. So if our gas utilization drop below 48%, we are literally burning money. As you must be knowing, the utilization, each 1% drop costs a huge amount of coke. That is around, if you want to quantize, it's in between 6 to 7 kg per ton hot metal. So you can imagine that is a big amount. So coming to our next slide about the data landscape, the telemetry fusion to find pattern. We fused FMCW radar mapping, mass spectrometry and isotherm modeling to build this digital twin. So this fusion engine rather inject 3D point cloud every 45 seconds and full spectrum chemical data every 10 seconds. So it's like giving the furnace an MRI every minute, every minute. So you can imagine the challenge behind it. So now coming to the top inside one, that is the permeability cliff. This graph is critical. We call it the permeability cliff. If your fines ratio exceeds 6%, permeability doesn't just dip, it collapses. This triggers catastrophic channeling and sends your delta P spiking to 2.3 bar. So coming to our next slide, which is a matter from top inside 2, that is the elephant foot paradox. An impermeable dead man might look stable on your top telemetry, but it's a silent killer. It forces molten iron radially outward, causing elephant foot erosion in the hearth. So this can jump your wall erosion rate from say 5 mm a year to critical 25 mm per year. So coming to our next insight, that is about the alkali. Mm, so as you must be knowing, the alkali amplification uh, is one of the important impurities in the furnace blast furnace. So a teeny increase in alkali or zinc act like a chemical glue, creating massive internal scaffold in the upper stack. So if your input has hit 4.0 kg per ton hot metal, you are looking at 450 thick scaffold and an 18% loss in the draft. So now coming to our next slide, which is about a deep dive one, and this is about a PSPP and refractory. So failure damage is not just on the surface; it starts the grain boundary where the zinc forces its way into the carbon brick. This zinc intercalation makes the brick brittle, causing thermal conductivity to plummet and leading to premature catastrophic heart failure. So now coming to our next slide, which is on about deep dive 2, and this is about a delta P trend analysis. The delta P equation is our definitive precursor to a disaster. So look at the traditional transition from the stable descent to hanging. So when that pressure differential hits an upward slope and the stock line flatliness, so you are minutes away from an explosive slip. So coming to our next slide about the root cause analysis. So this pathological channeling do not blame excessive blast volume for channeling. The root cause is fine segregation at the throat. Faulty radar distribution create low resistance path at the wall. So these lifts particle and causes severe thermal shock of our furnaces. So coming to our next slide, which is about a state diagram about the cohesive zone topography. We want to live in the emerald zone. That means maintaining a low inverted W profile for our cohesive zone. So these geometry act as a master gas distributor, ensuring over 50% gas utilization and high indirect reduction. So now we must have to correlate the things to find out alignment. So this slide is about the Korean matrix, the web of the influence, silicon and control. All are basically tightly coupled. So by tracking this correlation, we get a 4 to 5 hour warning window on the hearth thermal state. So if you find that fines goes up, your gas utilization drop within 2 hours was the link. Slide. The next upcoming slide is about the predictive forecasting, and which is on the closing the loop. So we are now using XG Boost model to ingest over 2000 data points. Now this machine learning tool can forecast a thermal collapse 8 hours before it happens, giving us time to adjust the raceway, flame temperatures and protect the taphole too. So now coming to our next slide, which is about intervention protocols, and which is very important measure that need to be addressed. So the diagnostic matrix, when the telemetry figure we act a peripheral temperature spike means we open the snot valve, sluggish descent means we lower alkali or an extra coke, block tears mean we immediately raise the blast temperature and charge blank book to restore the hearth. So now coming to the synthesis of the system, here the equilibrium equation, if you look into diagram, that every irregularity is just a failure to balance downward gravity against upward aerodynamic. So your burden mass promotes descent while mass pressure and liquid buoyancy fight it. So keeping the delta P balance is the only way to avoid pathology. So the what is the final imperative? So final imperative says that the prevention at the top stability is 1 hour lost before materials even enter the throat. So perfecting burden distribution is the ultimate non-negotiable cure, while active radar control and strict fine screening, and we will add 2.5 years of life to this furnace by monitoring in